Hi, we're Group 50 and we are the Smart Home Assistant. Our team members are Brian Okabar, Rob Brokaw, Tom Murphy, Tom Ray, and me, Nitin. Our advisors are Kian Nguyen and Ryan Price from Interactions LLC.
Smart home assistants are a rapidly growing field of modern technology. Currently, we see Amazon Echo and Google Home dominating the market. While these devices work well, they are limited in terms of other devices they are compatible with and are very costly. We intend to make our smart home assistant use open source software, so users can have freedom to decide what devices their assistants are compatible with and what functions it implements. There are three main components to our project. The automatic speech recognition subsystem is what converts the speech input into text. The natural language understanding unit maps the text to an intent so that commands can be said in multiple ways. Finally, the intent will be paired with an action that makes an API request to a Philips Hue bridge, effectively controlling a Philips Hue smart light. We used a Google Cloud Ubuntu server as most of our software worked best in an Ubuntu environment. We used Rasa to create an NLU and map intents to actions. We used Caldi as the ASR. Our software was written using Python 3 to use common libraries and Bash scripting to execute and weave together processes server-side.
The implementation and process flow of our smart home assistant is as follows. First off, we have Google Cloud Server, where we initiate a TCP connection so that we can do our call to online decoding, and another connection so that we can use the Rasa core system. On the Raspberry Pi, we use speech to pipe to the Caldi TCP connection for online decoding. Next up on the Raspberry Pi, Rasa takes the text from the Caldi decoding and sends it as a request to the Rasa Core API. After that, the Rasa NLU will process the information and classify intent. Next up, the intent will be mapped to an action, which will later be applied to a smart device. That device, being the Philips bridge, will be able to request an API, and after that, that request will tell the bridge what state to affect in the light bulb.
We faced many hardships over the course of the semester. Initially, our Philips bridge was producing connectivity issues during our setup phase. Additionally, the Philips developer account that you need to set up in order to get access to some of the API commands was a little troublesome and their documentation was unclear. And some of the libraries for open sourced ways of connecting with it were antiquated. Overall, gaining the Philips Hue bridge and other hardware components became a problem due to the COVID pandemic. It increased our shipping times, caused us to get our components late, and also gave us the inability to meet in person. Because of shipping delays, it caused us to gather all the components in different locations instead of a central one, making it hard for everyone to come together and to troubleshoot all the issues with a full working system. On the software side of things, Caldi had compilation issues when we first started to try its viability as our ASR unit. We found the method we needed to use for online decoding through a TCP connection. This allowed us to stream live audio into our system to be processed. Rasa was difficult, if not nearly impossible, to get up and running on the Raspberry Pi. This caused us to build many of the dependencies from source, such as TensorFlow and SciPy library, and Rasa itself. This is due to the architecture differences between a CPU and a common desktop versus an ARM-based processor, which is in the Raspberry Pi. Python wheels are built package format, which is very close to an on-disk format. Many common libraries are not supported for ARM-based processors, nor are there Python wheels built in order to increase the ease of installation of dependencies. Lastly, we face great difficulty when trying to connect to the Light Hue remotely. This is due for the need of authorization to gain remote access to the APIs from the developer resources of the Philips Lighthue. Since an API token, which is used to authorize a third-party user remote access to the Philips bridge, cannot be provided, the system has to run locally and on the same network as the Hue bridge. This caused difficulties since our code was hosted on a Google Cloud server, and we did this to increase our processing time for our speech decoding and our NLU classification.
Results of our project. Overall, we were very happy with how the whole project turned out. The ASR and NLU worked perfectly on their own, and once we found a way for them to work together to create our SLU, spoken language unit, their performance was still the same as they were apart. After running through multiple tests, and just seeing if Caldy could recognize simple phrases, checking the total time it took to control a light bulb from the time we speak, we were able to fine-tune the SLU in order to maximize its efficiency. This involved fixing phrases that were unnecessary for the main functionality of the Philips bulb. Raspberry Pi also gave us a very easy-to-use interface, which mimics our Google Cloud server, so this adds to the goal of making this open-source software easy to use and accessible to all. Future hopes of our project are to integrate more actions for the Smart Home Assistant that can be used with other parts of the Philips Hue bulb, add additional code to increase the customization and the capability of our control device, to find other components with API accessibility that can be controlled via RASA, develop an easy-to-access portal so that people with little to no programming knowledge can use a GUI to interact with the Smart Home Assistant. In this demo, we'll be demonstrating our Smart